Hi everyone, today I am going to start a new tutorial series on Delft 3D FM model. Basically this tutorial will be based on storm surge modeling. Previously I uploaded one tutorial series on HEC-SMS modeling. Since I'm working on this modeling right now, so I'm going to create a tutorial series on this modeling. So if you are working on storm surge modeling, or if you are interested in storm surge modeling in future, this tutorial may help you improve your knowledge on this modeling package and in this field of research as well. So there are several software packages that can model storm surges and also for hurricane as well. So like Delft 3D can do that, Schism and AtCirc. These models are very prominent and popular right now. So I'll use Delft 3D model to generate storm surge modeling. And we know that no model can capture by this time, means fully capture, no model can capture fully that combined effect of rainfall and storm surge, because this field is still in developing stage. So in this tutorial series, I'll try to couple both module, because Delft 3D, it has a new module that can model hydrologic part, and previously it has that hydrodynamic part as well. So we'll couple these two together and see what happens. So this is the new topic. It will help us to improve our knowledge on compound flooding. That is the hot topic right now. People are jumping in this topic and trying to do research, and there are several papers coming up. So you can even read that as well. So what I'm going to do in this tutorial series, I'll develop a storm surge model from scratch, and I'll show how to run this model in Linux machine in parallel computational mode as well. So that needs several coding skills in what is called, it is shell script and MATLAB and Python as well, because we have to generate a lot of input files. So I'll show how to even generate that input files using different programming languages as well. So let's see what I'm going to complete within this tutorial series. So I'm just going to share some slides so that you have a previous understanding that what will be the objective and what will be the goal of this tutorial series, and you'll see. If you're interested, then you can finish it, otherwise you can just exclude. So here is the slide. Just I'm giving the tentative title for this one, that coastal processes through numerical investigation of compound flooding in the coastal transition zone, because you may have idea about the transition zone. Sometimes when we have flooding because of rainfall, and at the same time if we have storm or hurricane or cyclone, so what will happen? It will cover the flooding from the downstream, and at the same time if we have enough rainfall on the land, so combinedly we will have a stagnation that will stay longer than normal period. So that is called compound flood, and the zone or the area or the location where this happens, it is called transition zone. So this is the most critical location where we have to be careful about modeling and other issues as well. So let's see what I'm going to cover and what is the objective and this. The study area for this tutorial I'll cover here. So if you are familiar with the USA map, this is the USA, and here you can see the red block. So that is located in Louisiana, and here is the Texas, and here is Florida, Miami, you can see. So if I just zoom in, so that is the location. I'll model this entire boundary. It is a pretty big area, so that covers two lakes. So these are two lakes, and then we have a part of the Gulf of Mexico here. So I selected this part based on HUC, hydrologic unit code. So there are two HUCs. The first one is called Amit River. So that is the Amit River. So this shaded area is the watershed of Amit, and this one is called Tikfor HUC. So if we combine all this together, so these are just flowing to this lake Maurepas, and then it is also further draining into the lake Pontchartrain, and eventually it is just flowing to the Gulf of Mexico. So this area is very important because sometimes we have significant cyclones or hurricane from this side, and then we have rainfall here. So we'll try to find out the combined effect of storm surge and cyclone, right? So we have that is why our downstream boundary is here and the upstream is far away from the coastal zone. And here are the objectives you can see. So we'll develop a Delft-3D flexible mesh model, for the area known as Lake Maurepas watershed, and then we'll calibrate the model to rain dominated event. Because I'm calling it rain dominated because this flooding event has only rainfall. Still it has storm surge, but it is not that significant. So I'm just selecting that event for the calibration purpose. And then I'm selecting another event that has the surge dominated effect, because it is also a cyclone or hurricane that just brings all the water from the sea to the land, but there is no rainfall enough to generate the compounding effect. Then I'll validate the model after calibrating it if the model performance is enough to capture the combined effect of rainfall and the surge. That's why I'll use a third event or fourth event to validate the model, right? Those who have knowledge on calibration and validation, you know what is called calibration and validation, but I'll show here step by step and what are the most significant parameters to make changes while calibrating it. And then I'll simulate the model for various combinations to capture the compound flooding drivers, because we know what are the major flood drivers. Rainfall, it is one of the major flood drivers for inland, and then we have storm surge because of rainfall and because of wind and also because of pressure drop, right? And there are also other flood drivers because upstream inflow will come into our model domain. So we'll try to capture all these processes to develop this model to capture compound flooding. And then finally we'll describe and quantify the impact on the transition zone as well. So here you can see, for developing any model you need a grid or mesh, and then you need different types of data as well. The most important one is the bathymetry data, but for this one, what happened, you can't even find one data set for land and water. For the ocean or any river or any lake or any coastal areas, you need to have the bathymetry data because these are the depth, and then you have to collect the elevation data set. So that is what I did here. So I collected the bathymetry data from CONAD, the source is called CONAD, and then I combined that CONAD data with the elevation data. These are basically the LiDAR, right? And then for any hydrodynamic modeling, we have to have that roughness because it is the most sensitive and most important parameter. It may be Manning's roughness or it may be Chase's roughness, whatever it is. For this one, we are using the space varying Manning's roughness. So you can even generate the roughness from land use information. So we are directly exporting this data from another model at CERC because we have another model for this area, so we can easily use the previously processed data for roughness. So that is what our job is simple for this one. But for the upper part, we don't have that one because that at CERC model, it is only covering the ocean processes up to this one. So that's why the new task I'm doing here, we're just capturing the upper watershed as well. So we'll generate the roughness for this area and we'll combine with this one. I'll show how to do that. And then you need, right, the observation data set. So here we are lucky that we have enough data set for calibration and validation purpose. So you can see the map, we have water level data from NOAA. These are the NOAA stations. And then we have also the Green's water level CRMS. and this is another data set, and we also have USGS. We also have water level and discharge from USGS, and we also have high water marks. High water marks are there, so maybe you are familiar with this one. Once we have any flooding event, so what happens after any disaster or any event, after just 1 week or two, the surveyor visit the location and they try to find the mark on the trees or any buildings. These are the highest mark, but we can't even know that when this happens, right? But we can even see the marking. So that then they just collect this data, and this is called high water marks. So we can validate our model or calibrate our model if the model is generating enough high water for that location. So we have many, it is more than 300, so that will be very useful for calibration and validation purpose. What next? And after that you need to force the model, right, with downstream and upstream boundary. Since we are going to use a combined effect of rainfall and storm surge, so we need the rainfall, right? So we are using stage 4 radar data, and we are also using that QPE, which is called MRMS, multi-radar, multi-sensor data. It is a blending or mixture of observed and simulated data, and basically the radar data. So that's the most accurate precipitation product right now. And we'll also use the wind and pressure field from NCAR and also from NOAA. And then we can see the study area. So water, it's coming from the upstream streams. So these are the streams. So that's why we need inflow. So we are collecting this from USGS observation. And then our downstream boundary will be extracted from a regional model. So that is covering the part of the Atlantic Ocean and fully this Gulf of Mexico here. And for the calibration purpose, I already mentioned that we'll calibrate the model for 2 different events. So we are going to select a flooding event for 2016, and this event was mostly, you can see the radar image, was mostly from rainfall. However, on the right side you can see we'll also calibrate the model for Isaac that held in 2012, and it is basically it was mostly from storm surge, and the rainfall was not that significant. So we'll calibrate our model for these 2 contrasting event, and then we'll validate our model for a third event that has both effect. And here and next, if you have all this data set, you have to generate the mesh. It is the most important part of any modeling. So if your mesh means the computer will solve differential equation, right, at every node, and then it will just propagate to the upstream or downstream, whatever it is, whatever the computational scheme is, it based on the solver. Okay, so for this area we'll have, I'll show how to generate the mesh. You can see we have very coarse mesh at the very downstream here, and it's up to 3 kilometer, but you can't even imagine that it is 3 kilometer by your naked eyes. But on the left side you can see, if I zoom in the streams, it is very fine mesh I'm using here. I'm resolving the streams, which is very meandering and narrow. So the mesh size is 5 to 250 meter here on the land. So total number of element we have 500,000. See, it is around 500,000, and the node is around 250,000. So when I'll run the model, the computer will take like more than 2 days or more than even 7 days. So what I'll do, I have to split the modeling scheme into 30 or 40 pieces. Then I'll run the model in parallel processing, so that I'll assign 20 computer processor to calculate all together. So that will reduce the time to 20 hours at least. So that is huge. Okay, so what we have, and then after generating the mesh or the grid, whatever you call it, because this is called flexible mesh and these are called unstructured mesh as well. So here we'll use the precipitation for that event. If you have, because this precipitation, it needs another special format, so you have to write code in MATLAB or Python. So I already have that, so I've written the code, so I'll show how to do that. But the special thing for this precipitation input file is that it can't even solve at unstructured mesh. It needs structured mesh, so you have to supply another mesh which has to be like this one, rectangular mesh, and then you have to create that precipitation file for that structured mesh. However, for wind, this is the wind field and that is the pressure field. For wind and pressure you can even supply as ASCII file, so I'll show how to do that. And then we have another water level. This is the not water level, this is a discharge coming from upstream. So we have 8 points, total 8 points. So I'll show that, but here I'm just showing a sample, and here at the very downstream we have this water level boundary condition. So once you have all this forcing, then you can run the model, and then what it will look like. So it will look like this one. So I'm running this model for two different events. So the left one you can see it is for the 2012 event, and you can see the flooding, the surge from the storm, right? I run the model for 1 month, but here I'm showing only for few days. See, it is just flooding the entire watershed, and then we'll evaluate the performance of the model. And on the right side you can see it is not like 2012, because for 2016 mostly the flooding it's happened because of the heavy precipitation. So these are the two contrasting event. So once our model is ready for these two event, then we'll validate our model for another event. I just already mentioned that one. See, and then we'll try to test the performance of the model, right? We'll calibrate the model for 2016 first. Here you can see that, and we'll just find several locations within our computational grid. For example, we are calibrating this model for discharge. I'm selecting 2 points, and then we have the observation from USGS, and I'm just extracting the flow rate from the computation from the model simulation. Then I'm just comparing here. Still it needs some calibration because I didn't add the space varying roughness for the upper part. So I'll do that, and I'll show how to do that as well. And once our calibration is done, or still while calibrating, we have to even compare the water level as well. So we are comparing the water level for for 4 different stations here. These are also from USGS. And then see, I'm just comparing the high water marks. So in terms of 2016, the model performance is like its best, like 0.99 NAC. That means the model is perfectly capturing the high water, but still the performance is not enough to capture the entire hydrograph. So we have to fix that. And then I'll calibrate also the model for 2012. I already demonstrated the simulation animation. Here, see, for 2012, since the flood is coming from the downstream side, I'm comparing the water level at 2 NOAA stations. Here you can see the model is perfectly capturing the peak, and the model performance is pretty impressive, right? And then I'm also comparing, and I'll show how to extract this data and how to process all these things using different scripts. So I'll show all these processes so that you can even reproduce everything, and you can implement that in your research or modeling. There are many points. We're comparing and we're testing the performance at multiple locations, and if we have enough performance, then we can easily validate the model, and we can use that model in predicting future event or future planning. Whatever we need, we can even do that, right? But still, see, for 2012 the high water marks, because the model is not clearly capturing this one, because I used the very coarse mesh here, 2 kilometer or 3 kilometers. So I'm going to refine this mesh so that it can capture every single peak. So that's the thing we have to modify. So here is the calibration. So this is called calibration. We have to fix that, and once we have the model ready, then we can use that model, right? So this is what I'll basically show you in different segment of the tutorial. So if you are interested, you can even continue viewing this one, and then you can try to make your own model. And if you have any query or any confusion or any question, you can ask me in the comment box, or you can send me email, so that will help me also to understand other problems and how to solve that. We can even figure it out. Okay, so thank you very much.